Hi, welcome back to educator.com. Today's lesson in general chemistry is on chemical reactions. Okay, let's go over the outline. We're first going to talk about something very fundamental to all of the physical sciences, and that's the law of conservation of mass. And we're going to see that in order to obey the law of conservation of mass, anytime we have a chemical equation, we have to make sure that it is completely balanced. After discussing this, we'll then go on to something we call chemical equilibrium, because chemical equilibrium is going to be very applicable to our discussion of reactions in solution. And the solutions that we're specifically talking about are electrolyte solutions, non-electrolyte solutions, and etc. After talking about electrolytes and non-electrolytes, we're then going to dive into a couple of different reactions that can occur in aqueous solutions. The first one is what we call single replacement reactions. The second one is what we call double replacement reactions. The third one is neutralization reactions, and the fourth and final one is going to be reactions that produce unstable compounds that are going to further decompose and form other compounds we could not initially predict. And so when this section is done, we're going to be able to predict the compounds that are formed for many of these types of reactions. We'll wrap up the session with, of course, our summary, followed by a pair of sample problems. Okay, let's go ahead and start. The law of conservation of mass is fundamental to all of the physical sciences, and we always will be obeying this in chemical reactions. And basically, the law of conservation of mass tells us the following, that matter can neither be created nor destroyed. In other words, what you have, you're going to have permanently, and it's coming from other sources, and you're never going to truly eliminate it or get rid of it. But matter, as we know, can be transformed into different states, etc. If we were to translate this into a chemical reaction before and after, the law of conservation of mass basically tells us the following, that the total mass before a reaction is going to be equal to the total mass after a reaction. In other words, the total mass of what you start with equals to the total mass of what you end up with. So let's go ahead and look at a typical way of representing a chemical reaction. Basically, the general format of a chemical reaction is the following. We have the reactants on the left side of the arrow, and we have the products on the right side of the arrow. And we can go ahead and verbalize this the following way, that A combines with B to form C and D, or A and B yield C and D, or A and B mix C and D, whatever you're more comfortable with. And basically, if we were to apply the law of conservation of mass, this is telling us the following, that the total mass combined of A and B will be equal to the total mass combined of C and D. All right. In order to obey the law of conservation of mass, we have to do what's called balancing a chemical equation. And you're going to be using this from now on pretty much in every lesson. And this is one of the most fundamental parts of general chemistry that you want to learn to master early on. So when we balance a chemical reaction, let's go ahead and look at the following. N2 plus H2 goes on to form NH3. We want to look at the number of elements on both sides of the equations. For example, here we notice that there are a total of 2 nitrogens on the left side, but there's only 1 nitrogen on the right side. In addition, on the reactant side, there are 2 hydrogens, and there are 3 hydrogens on the right side. So we say that this is an unbalanced chemical reaction. And we never want to leave a chemical equation unbalanced. And so the way to go about this is the following. We're going to put what are called coefficients right in front of each of the molecules to go ahead and balance this. And I want to give you, and the coefficients are usually going to be whole numbers. I want to give you a couple tips. Whenever the reactants are all homonuclear, it doesn't matter which element you try to balance first. And what I mean by homonuclear is that it's basically a compound composed of just one element. So one element type only. So examples of homonuclear would be N2, H2, O2, Cl2, etc. So those are, again, what we call homonuclear. So a lot of the time is trial and error, so let's go ahead and start. So N2 plus H2 goes on to form NH3. So what I like to do, I'd like to maybe balance nitrogen first. Again, it doesn't matter what order you do it in. So I'm going to go ahead and put a 2 in front of NH3. And then I ask myself, okay, I got now 2 nitrogens on the left. I got now 2 nitrogens on the right. So the last thing to fix is hydrogen. Well, now I have 2 hydrogens on the left, and I got 6 hydrogens on the right. And so basically, we ask ourselves, what multiplied by 2 is going to give us 6? And so the answer is going to be 3. And so my balanced chemical equation is going to be N2 plus 3H2 goes on to form 2NH3. And always, this is very important, always double check your work to make sure that you've done the balancing correct. And as you can see, we have 2 nitrogens on both sides of the equation, and we have a total of 6 hydrogens on both sides of the equation. Okay, so before we move on, another thing I just want to point out is the following. When you have the coefficient and a subscript, you just multiply them together to get the actual number. That's how we get 6 hydrogens there. So coefficient multiplied by the subscript. Okay. Let's go ahead and now move on to another chemical reaction where the reactants are not both homonuclear. So for example, CH4 plus O2 goes on to form CO2 and water. So we have CH4, which is going to be what we call heteronuclear. That is, the compound is made up of more than one element. So my advice I usually give is the following. You always save the homonuclear element, the homonuclear reactant for the last step. And that's going to make your life a lot easier. All right, so let's go ahead and try to balance this. So again, it's CH4 plus O2 goes on to form CO2 and H2O. So I'm going to save oxygen for the last because it's part of a homonuclear compound. And so I'm left with either carbon or hydrogen to start with. And again, it doesn't matter for those. So let's just go ahead and pick carbon. Well, carbon, we have 1 on each side of the equation. We have 1 in the CH4 and we have 1 in the carbon dioxide. So carbon's already balanced. So the only thing remaining is hydrogen now to work with before we tackle oxygen. On the left side of the equation, I have a total of 4 hydrogens. And on the right side of the equation, I have a total of 2 hydrogens. So I'm going to put 2 right in front of water. Now my hydrogens are balanced. I got 4 on both sides of the equation. Remember, multiply the coefficient by the subscript. 2 times 2 gives us 4. All right, now we can go ahead and tackle oxygen. I have a total of 2 oxygens on the left. And I have a total now of 2 oxygens in carbon dioxide. And I got a total of 2 oxygens in water. Remember to carry through the coefficient, okay? So actually I have 4 oxygens total on the right side of the reaction. So I'm going to put a 2 right in front of O2, and that gives me a total now of 4 oxygens on both sides of the reaction. And so that's it. That's our balanced chemical reaction. Another piece of advice I usually give students is the following. Balancing chemical reactions can be very frustrating, and you don't always get it right the first time. A lot of it is trial and error. So if going by one element the first time doesn't work, try another element until you get it. But remember, it always can be balanced. That's a fundamental law of nature, okay? It always can work. All right. right now I want to introduce to you a chemical reaction where sometimes the coefficients that we're going to use initially are not going to be all whole numbers. Instead, the coefficients that we're going to be using are going to be fractional. Okay? So remember what we have to do. It's going to be the coefficient times the subscript. And that's going to give us the total number of that element in the compound. So total number of element in compound. Okay, so let's go ahead and balance this. So C2H6 plus O2 goes on to CO2 and water. So I have 2 carbons on the left side and only got 1 carbon on the right side. And so I'm going to go ahead and put a 2 in front of CO2. Now my carbons are fixed. Remember that I'm leaving oxygen for last because oxygen is part of a homonuclear compound. So what we have to do now is fix hydrogens. I have 6 hydrogens on the left and I have 2 on the right side. And so then we ask ourselves, okay, what coefficient, what number times 2 is going to give me 6? And so that's going to be a 3. And so now my hydrogens are fixed, 6 on each side. And so now we have the following. C2H6 plus O2 goes on to form 2CO2 and 3H2O. Let's go ahead and look at the oxygen count right now. I got 2 oxygens on the left side, and here on the right side I have a total of 4 oxygens in CO2, and I have a total of 3 oxygens in water. So that means I have a grand total of 7 oxygens on the right side, and only have 2 on the left side. So this is when we have a case of an even odd number. If you look at the previous examples, we've always had an even number on one side and an even number on the other side. In that case, it's always convenient just to use a whole number. But when you have an even odd pair like this, there's going to be a little trick we're going to do, okay? Basically, you ask yourself the following. So you see that I'm shy of oxygens on the left side. So we have to ask ourselves, okay, so what coefficient times 2 is going to give me 7, right? So basically, 2 goes downstairs, 7 goes upstairs. And so it's very simple, everybody. When you have an even odd pair, you will always use a fractional coefficient. And basically, the bottom number is going to be the subscript from the homonuclear compound. And the top number is always going to be the greater number, what you are trying to get the homonuclear compound up to. So once again, when you have an even odd pair, use fractional coefficients. And so the fractional coefficient I'm going to use is 7 over 2. Okay. Now remember a few sessions back we talked about Dalton's atomic theory. And part of his theory was that elements combine in small whole number ratios to form compounds. What that means is the following. We never want to leave a chemical equation in a fractional form. In other words, what we're going to do right now, we're going to eliminate the fraction and we're going to be left with nothing but whole numbers. So, the fraction we have is 7/2. Well, if we want to get rid of a fraction, we simply multiply by its denominator. But I just can't multiply oxygen by 2. If I change one element, I got to do it proportionally to everything. And so my grand and final answer is going to be the following. It's going to be 2 C2H6 plus 7 O2. And that's going to go on and form 4 carbon dioxides and 6 waters. Okay, and this gives us our balanced chemical equation with no fractions. Let's just go ahead and do one final check. Make sure we've done it right, and let's go ahead and see if we have the same number of elements on each side. Okay, so I got 4 carbons total here, 4 carbons total here, so carbons are good to go. I got 12 hydrogens here, and I have 12 hydrogens here, so hydrogens are good to go. And finally, I got 14 oxygens here, and I got, let's see, 8 oxygens in Cl2 and 6 oxygens in the water, giving me a grand total of 14 oxygens. So as you can see, this method does work. And again, the final thought is to never leave a coefficient as a fraction. Okay, so now that we've learned how to balance chemical equations, let's move on to the next topic of the session, and this is what we call chemical equilibrium. Now, when an ionic compound fully dissociates, and what I mean by fully dissociates is that it completely breaks up. It forms the individual cations and anions. Whenever this happens, we use a single arrow in the forward direction. Okay, so for example, hydrochloric acid is going to be fully dissociating when dissolved in water, and that's going to break up into its respective cation and anion. All right, but not all ionic compounds do this. A lot of ionic compounds really incompletely dissociate, which means they don't fully break up into cation and anion. When this occurs, we use a new type of arrow. It looks like a pair of opposite arrows, everybody. And this is what we call an equilibrium arrow. What the equilibrium tells us is that the reaction is reversible. In other words, let's look at HF. As hydrofluoric acid breaks apart, in other words, as we move in the forward direction, H plus and F minus instantaneously form. However, look at the reverse arrow. Let's go ahead and translate that. What that is telling us is that H plus and F minus are going to somehow find each other again. They're going to recombine and reform the original hydrofluoric acid molecule. So this is what we call dynamic equilibrium. That is, it's a constant process. It is not static whatsoever. And basically, both the forward and the reverse reactions happen simultaneously. In other words, as soon as a compound dissociates, the ions are going to recombine into the original compound. Again, you're going to call this an equilibrium arrow, and we're going to be using this quite heavily in the latter half of this general chemistry class. Okay, so now we're going to talk about specific compounds when they dissolve in water, and they're called electrolytes and non-electrolytes. You know, when you hear the word electrolytes, it obviously, sounds like electricity or electron. And basically, electrolytes are going to be ionic compounds that form ions when dissolved in water. For example, we can go ahead and take a salt, table salt, sodium chloride. And so sodium chloride is going to dissociate and form the respective ions, sodium cation and chloride anion. And the following is going to be a fundamental requirement for a solution to be conductive. And basically, a solution has to have free ions in order to conduct electric current. That's why they call them electrolytes. Okay, strong electrolytes completely dissociate. And so for strong electrolytes, which completely dissociate, we're going to use a regular single arrow in the forward direction. Weak electrolytes incompletely dissociate. So remember, going back to the previous slide, for ionic compounds that incompletely dissociate, we used a equilibrium arrow. Okay? And finally, there are compounds that, when dissolved in water, they do not form ions whatsoever. And so these are going to be non-electrolytes, and these are going to be typically molecular compounds, everyone. For example, if you take ordinary, like glucose, for example, C6, H12O6, and you go ahead and dissolve it in water, you don't form individual ions. It just becomes aqueous. Okay, so you see that there are no ions whatsoever, so glucose is going to be a non-electrolyte solution. All right. Now that we've gotten those vocabulary terms out of the way, what we're going to do right now, we're going to study specific types of aqueous reactions, and we're going to learn how to predict the products. The first type of aqueous reaction is what we call a single replacement reaction, or also known as single displacement. And a single replacement reaction is going to always have the following general format. A, and this is usually going to be a metal, go plus B and C. Remember, this is going to be the metal, this is going to be the non-metal, usually, or the cation and the anion. Goes on to form ACMB. You notice that A has come in and essentially displaced B from its bond with C. And so we go on to form ACMB. So this is called a single replacement. Let's go ahead and look at a couple of examples. You take lithium metal and you react it with copper 2 chloride. Lithium is going to come in and knock out copper, and we form lithium chloride instead. And copper is going to also come out as copper solid. However, let's reverse the process. If we take copper solid and go on and react it with lithium chloride, we get no reaction at all. Let's go ahead and see why this is going to occur and how you're going to be able to predict this. So all of the experiments have been done already, and the results are summarized in what's called an activity series. And basically, an activity series is the following. You see that lithium is right at the first element. And we call lithium a very active metal. It can come in and knock out essentially any other element. Let's look at sodium. Okay, the way to use this activity series is the following. Sodium can knock out any element below it, but it cannot knock out any element above it. So for example, sodium will not be able to knock out calcium, but it will be able to displace magnesium in a single replacement reaction. Depending on your instructor, you may or may not have to memorize this activity series, so definitely be on the lookout for that. Okay, another very common type of single replacement reaction occurs between the following: a metal and an acid. So for example, when zinc solid is going to get dissolved in hydrochloric acid, we get the formation of zinc chloride and hydrogen gas. So essentially zinc has come in and knocked out hydrogen. Let's go ahead and see if we can find hydrogen on this activity series. Well, we know that zinc is going to be right here, and right below it is going to be H2. So yes, this activity series does predict that zinc is going to come in and displace hydrogen in a single replacement reaction. Now here's the thing. When hydrogen is displaced, it always forms hydrogen gas. Okay, so when displaced in a single replacement reaction, okay, it's going to form H2 gas. All right, so this is how we use an activity series for single replacement reactions. The next type of reaction we want to talk about is going to be called double replacement reactions, also known as double displacement. And basically, instead of one quote unquote knockout, two occur. Okay, so we're going to have two swaps, everybody. And I always like to show brackets with this. So basically, A is now going to hook up with D, and now C is going to hook up with B to form AD and CB. And please note how the cation always hooks up with the other anion, etc. All right, so an example of this is going to be the reaction between sodium chloride and lead 2 nitrate. So sodium is the cation. It's going to hook up now with the other anion, which is nitrate. And lead 2 plus is going to hook up with the other anion, chloride. And we get sodium nitrate and lead 2 chloride. Now, please note, this is very important when you do this, that the charges never change, especially for the transition metals. Remember when we went back to nomenclature and you learned that transition metals can have different oxidation numbers. So here, this is going to be lead 2 plus. There should be really a 2 there. Sorry about that. And so here in the product side, it's going to remain lead 2 plus. So please do not ever change a metal's charge in a double displacement reaction. So lead 2 plus is going to remain lead 2 plus. That's why it's PbCl2 and not just PbCl, for example. Okay, the next type of equation, though, something very related to this, is the following, and that's called a net ionic equation. And a net ionic equation is usually written to show the formation of the precipitate. Precipitate is just a fancy name for the solid that's formed in a reaction. And basically, a net ionic equation shows the formation of the precipitate, in this case lead 2 chloride, from its constituent ions. And that's basically going to be lead 2 plus combining with 2 chlorides. Okay, so it's always aqueous plus aqueous goes on to form the solid. All right, so now that we covered net ionic equations, how do you predict that a compound is going to be solid? Or how do you predict if it's going to remain aqueous in these reactions? So this is something you may or may not have to memorize also, so please be on the lookout for that from your instructor. And so this is what we call the solubility rules for ionic compounds. And basically this table is divided into 2 areas. First, the compounds that are usually soluble. So what soluble means is that the compound is going to remain broken up into ions and dissolved. So something that's soluble is going to be essentially AQ or aqueous in the chemical reaction. Okay, so you're going to find ammonium salts, group 1 salts, nitrates, etc. Now, what's important in this solubility table is to pay attention to the exceptions. For example, okay, acetates are usually soluble. So for example, sodium acetate will be aqueous in water. However, there are exceptions such as silver 1 plus and aluminum 3 plus. So while sodium acetate is going to be aqueous, silver acetate and aluminum acetates are exceptions, and they're going to be solid. That is, they're going to be insoluble. Okay, so you always got to pay attention to the exceptions. The same goes for the other side of this table. So compounds are usually insoluble. They're going to be remaining intact and not break up, relatively speaking. And so they're going to remain as solids. So carbonates, phosphates, etc. are going to be solids. However, there are exceptions. So something like magnesium carbonate is going to be mostly a solid in water, but an exception is ammonium. And so ammonium carbonate is going to remain aqueous in water. Okay, let's go ahead and apply another type of double displacement reaction, everybody. And that's what we call a neutralization reaction. A neutralization reaction always has a generic formula. An acid is going to react with a base, and it's always going to form a salt, water, and it's always going to give off heat. So anytime you mix an acid and a base, it's going to feel warm to the touch. Okay, so a typical reaction would be between hydrochloric acid and sodium hydroxide. And neutralization reactions are going to be typically double displacement reactions. So hydrogen is going to hook up with hydroxide. Chloride is going to hook up with sodium. Okay, so let's do the salt. The salt is going to be sodium chloride. And from the table of solubility rules, which we just covered, this type of chloride is going to be soluble, which is aqueous. Okay, you see that when hydrogen combines with hydroxide, that's essentially going to form water, and that's going to be liquid. Okay, so there we have it, a double displacement reaction in the form of what we call a neutralization reaction. Let's do one last example, and that's going to be between sulfuric acid and potassium hydroxide. Okay, sulfate is going to hook up with potassium. Again, hydrogen is going to hook up with hydroxide. Okay, so this time the salt is going to be potassium sulfate, And I need 2 potassiums to balance sulfate's 2 minus charge. And looking at the table of solubility rules, that's going to be aqueous. And again, I'm going to always form water. Okay, let's go ahead and balance it. So I'm going to need 2 potassium hydroxides to go ahead and react with the sulfuric acid. And I'm also going to form 2 waters as a result. Remember, always balance your chemical reactions, everybody. All right, so we saw that a neutralization reaction is a type of double displacement reaction. Now, there are a few exceptions where using the table of solubility rules and simply going by a generic format for double replacement does not work. These 3 reactions here are going to form compounds initially that are unstable. These unstable compounds are going to in turn produce additional products, which we just can't predict. So we're going to now introduce these to you. The first type, number 1, is going to be the reaction between a metal carbonate, and this is usually going to be a group 1 metal, reacting with an acid, HA. And usually A is going to be the following: Cl, Br, iodine, nitrate, and also can be sulfate. Okay, so sulfuric acid, nitric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, etc. Okay, so these are what we call the strong acids. And again, depending on your instructor, you may have to know a number of different ones. So please definitely be on the lookout for that. Okay, when we do the double displacement format, we're going to get, H2CO3 carbonic acid in combination with Ma aqueous. Now, it doesn't stop there. What happens is the following: that carbonic acid is actually unstable in water, and it's going to decompose to form CO2 and liquid water, everybody. Okay, so that's one example. So again, a metal carbonate reacting with a strong acid goes on to form carbon dioxide gas and liquid water. Similar to metal carbonate reacting with acid, we're also going to see metal sulfites reacting with acid. Okay, so very similar. We're going to form instead H2CO3. We're going to get H2SO3. Okay, sulfurous acid in combination with the salt. Sulfurous acid, like carbonic acid, is unstable in water, and it's going to form not CO2 but SO2 in combination with water. Okay, everybody, so once again, it's going to be a group 1 metal sulfite reacting with strong acid to give you sulfur dioxide gas and liquid water. Okay, the third and final example that's an exception is going to be the following. It's going to be an ammonium salt, where X is usually a halide. It's going to be the ammonium salt reacting with a metal hydroxide, and again, this is usually going to be a group 1 hydroxide. And when you do the double displacement, okay, the M is going to hook up with X, and ammonium is going to hook up with hydroxide. And it turns out that ammonium hydroxide is unstable in water, and it's going to decompose and form aqueous ammonia and liquid water. So once again, the third exception, something we just can't predict, is the following. It's going to be an ammonium halide salt in combination with a group 1 metal hydroxide, and you're going to form ammonia, NH3, in combination with liquid water. All right, so that pretty much covers solutions that are occurring in aqueous environments. Let's go ahead and summarize what we learned. We started off talking about the law of conservation of mass, and remember, a big implication of the law of conservation of mass is that we always have to balance any chemical equation. We went on to discuss electrolytes, and we learned that strong and weak electrolytes are going to each dissociate to different extents when dissolved in water. And we learned several rules. We saw an activity series, we learned the table of solubility rules, and we learned the 3 exceptions that we can use to help us to predict the product of any reaction that occurs in aqueous solutions, especially single replacement, double replacement, and neutralization reactions. Okay, let's go ahead and tackle some sample problems, everybody. So here I've presented to you the reactants, and I want you to come up with the products, and of course, always balance the chemical equation. All right, let's go ahead and look at this. So we have a zinc carbonate, okay, that's going to be a metal carbonate, reacting with a strong acid, H2SO4. So that's one of the exceptions, everybody. So what's going to happen is the following. We're going to get zinc sulfate, okay, and that's going to be aqueous. Use your table of solubility rules. And remember, and where this is going to form not H2CO3, but H2O liquid and CO2 gas. Remember, H2CO3 is going to be one of those unstable compounds in water, and H2CO3 we saw breaks up into liquid water and CO2 gas. Okay, let's go on. Next one, ammonium bromide reacting with lead 2 acetate. All right, so in this case, lead is going to now hook up with bromine, and ammonium is now going to hook up with acetate. So this is yet again another double displacement reaction. Okay, so when we go ahead and draw the products, let's go ahead and do ammonium now with acetate. So NH4, C2, H3O2. Okay, and lead 2 bromide. Remember, lead 2 plus remains lead 2 plus, everybody. Okay, and let's not forget the physical states. Ammonium acetate is going to be aqueous, and lead 2 bromide is going to be the solid. And most importantly, always balance your chemical equation. So I'm going to need 2 of these, and I'm going to need 2 of these for my balanced chemical equation, everybody. All right, next one. Okay, potassium nitrate, aqueous, reacting with copper 2 chloride. Okay, so this is going to be another example of a double displacement reaction. So, okay, nitrate is going to hook up with copper, and potassium is going to hook up with chlorine. So, we're going to get KCl. And when you look up the table of solubility rules, that's going to be aqueous, reacting with copper 2 forming copper 2 nitrate. And when you look up the table of solubility rules, that's also going to be aqueous, everybody. So this is an example of a double displacement reaction that forms no precipitate, which is not too uncommon. All right, final example of sample problem 1. Lithium sulfate reacting with silver nitrate. Let's go ahead and do the double displacement. Okay, so lithium is now going to hook up with nitrate, and sulfate is going to now hook up with silver. All right, so when we go ahead and do this, we're going to get lithium nitrate, and that's going to be aqueous when you use the table of solubility rules, and silver sulfate. Okay, and silver sulfate, everybody, is going to also be aqueous when you look up the table of solubility rules. All right, we got to balance this, so this is going to be 2 of these and 2 of those, everybody. Oh, I forgot, for the third example, the potassium nitrate reacting with copper chloride, I left it unbalanced. Okay, shame on me. So again, let's go ahead and fix that. So we're going to need 2 of these, everybody, and 2 of those. All right, so I hope this sample problem 1 was really testing your ability to not only predict the products, but also the physical states, in addition, of course, to balancing. Okay, the final set of sample problems, everybody, involves the following. I've seen a lot of tests, everybody, and a lot of the times you have to translate from a sentence or a phrase into a chemical equation. So this is really testing your ability of nomenclature also. So this is a nice cumulative type of problem, everybody. Solid zinc, okay, reacts with aqueous lead 2 nitrate to form aqueous lead 2 nitrate, zinc 2 nitrate, and solid lead. Let's go ahead and translate it. Okay, so zinc solid reacts with lead 2 nitrate, going on to form zinc 2 nitrate, aqueous, and solid lead. Okay, let's go ahead and balance this. So we're going to need 2 zinc nitrates. Oh no, it's going to be zinc 2 nitrate, I'm sorry. So this is going to be 2 of these. Okay, I'm going to erase that coefficient, everybody. Very sorry about that. And that's, yeah, so my balanced chemical equation is good to go. Okay, so this is an example of a single replacement reaction, and everybody, if you go ahead and look up the table, the activity series, zinc will come in and knock out lead, everyone. Okay, second example, solid iron reacts with molecular chlorine gas to form solid iron 3 chloride. Okay, so solid iron reacts with molecular chlorine. Remember what we mean by molecular chlorine? Okay, that's going to be Cl2 gas, not just Cl. And that's going to go ahead and form solid iron 3 chloride, FeCl3 solid. All right, let's go ahead and balance this. Well, iron's good to go already. I got 1 on each side, but I got 2 chlorines on the left and I got 3 on the right side. And so we can go ahead and simply put a 3 in front of the Cl2 and a 2 in front of the iron Cl3. And finally, I'm going to need 2 irons. Okay, so this is again an example of an even-odd pair where you could have used the fractional coefficients, everyone. That would have worked too. All right. This is an example, everybody, of what we call a combination reaction, where we have the form A plus B goes on to form AB. Once again, a combination reaction. Okay, last example, everybody. We have solid barium peroxide forming solid barium oxide and molecular oxygen gas. Let's go ahead and write this and balance it. Okay, so we got solid barium peroxide. And you're told that this forms solid barium oxide in combination with molecular oxygen gas. Remember, molecular oxygen, everybody, okay, very important. So that's going to be O2. All right, so my bariums are good to go. So the only thing we got to balance are the oxygens. So I got 2 oxygens on the left, I got 3 on the right. Let's go ahead and put a 2 in front of BaO. And that's going to give me 4 oxygens on the right side now and 2 bariums. And all I got to do is put a 2 in front of there. So I got 2 bariums on both sides of the equation. I got 4 oxygens on both sides of the equation, everybody. And this is what we call a decomposition reaction, where we have one compound AB essentially dissociating into A and B. So one compound forming multiple products. Okay, so this is a nice cumulative exercise, everyone, where it really tests your ability, your knowledge of the nomenclature, and of course to balance a chemical equation. All right. Thank you very much for your time, and I'll see you next time on educator.com.